Cities are one of our greatest inventions. They bring us together. But as more and more of us want to live in them, we need to find ways to make them greener and more sustainable.
Oh, this is massive. The question is, how will scientists, designers, entrepreneurs and engineers reimagine our cities to answer the problems that we're facing?
I'm Dr. Nij Lal, and I want to investigate what sort of cities we'll be living in.
It's a long way down.
It's a long way down if you're not in a machine.
I'll see the giant mechanical worms creating vast spaces under our feet.
Not long from now, there'll be streams of people coming in here and catching their trains wherever they're going around Sydney in the very near future.
I'll discover how your next office block might be built out of homegrown timber.
We can grow one of these buildings in less than a day very happily.
And I'm off to visit what's been billed as the greenest airport in the world.
So it's greener, faster and stronger.
Correct.
As I take a look at the technology that's shaping our urban future. We all hate being stuck on the daily commute. Sitting in traffic jams, waiting for crowded trains. Yet in Australia, our major cities are set to grow by nearly 10 million in the next 30 years.
So how people get around will become increasingly difficult.
But until we have flying cars, we're getting pretty congested.
One possible answer to this problem is right here in the middle of Sydney, deep underground.
I've been given special access to the largest public transport project ever undertaken in Australia. It's like a vast underground factory down here.
And then your glasses. Welcome, Christian Dott, Construction Manager for the TBM tunnels on Sydney Metro.
Awesome, nice to meet you. I'm Nij.
Our breakthrough is about 5 minutes away, so let's head on down.
Sounds great, thanks.
For 12 months, teams have been tunnelling beneath the harbour floor, one of the most complex parts of the project.
Oh, this is massive.
You should wait until we get around into the main cabins. This is just the temporary ventilation tunnel and temporary services tunnel.
The plan is to deliver more than 66 kilometres of new rail and 31 new metro stations. And this is one of them.
This is the line, this is the train line.
This is the train line.
Ah.
So this will be one platform. So the up line, the train heading from Marrickville to Chatswood, this will be the station platform where that train will stop.
So what, like a couple of years from now, people are just going to be on here waiting for the train?
That's right.
But the success of this monumental project hinges on the accuracy of a specialised tunnel boring machine known as a TBM.
So our TBM today will break through at the far end there through the white dot. We'll push the TBM through, back into the other side and continue on the way to Barangaroo.
It's been navigated here using a specially designed laser target system. And, all going to plan, it's about to emerge through that white target.
Here today there's going to be a 7 metre diameter TBM coming through. It's the size of two A380 aeroplanes. It's 160 metres long, it weighs over 1,000 tonnes.
It's like a giant earthworm.
It is like a giant earthworm.
I can hear it coming through.
That thundering noise, that's the cutters on that TBM. They're fracturing that rock as the machine will break through.
There's a little bit falling off the wall. I can feel it in my belly, in the ground. It's starting to shake a little bit.
That's about to go now.
Bang on, it's bang on.
Right with it this evening. You see the water suppression we use to help control that dust. We also have a dust extraction machine on the TBM.
Tunnelling projects like this can be hugely expensive, time-consuming, and often go over budget. But they're just one part of a movement towards resilient and sustainable infrastructure that has to work for us now and in the future. There's still a way to go on this project, so I'll be back in a few weeks to see what they've done to this hole. We use 30 million cubic metres of concrete every year in Australia. And it's one of the most common building materials in the world. But it has one downside.
For all its glory, it comes at a high price.
Concrete produces around 5% of the world's carbon emissions, more than double that produced by aviation, according to the International Air Transport Association. I'm off to see what's been dubbed the greenest airport in the world. This huge 20,000 square metre slab is destined to be an airport taxiway, so strength and integrity are critical.
But this is far from a conventional concrete pour. It's not even conventional concrete. It's geopolymer concrete, or green concrete.
Early studies have found this green alternative produces 50% less emissions than regular concrete. But it's still really only being trialled at this kind of scale.
John.
Good to meet you.
See ya.
One of the people behind the innovation is Technical Director John Day.
Well, we're paving along at approximately a linear metre a minute.
His company is one of a handful around the world experimenting with green concrete.
Road paving machine extrudes the concrete out the back of the machine.
I've worked with concrete before. I poured a 30 centimetre slab in my backyard for my beehive. And this looks just the same.
And so how is handling geopolymer concrete different to handling conventional concrete?
Well, on the job, it's got slightly more internal cohesion. So I guess the way to put that would be it's slightly stickier. It's a little bit harder to get it there, but once you get it there, it stays there.
So how do you make green concrete? And why is it less polluting? Just like regular concrete, green concrete is made up of gravel, sand, and a paste that binds it all together. For this project, the gravel is sourced locally.
Blast guard tree, area secure.
Everyone ready up there?
Yeah, mate, all good to go.
5 seconds till firing.
And it's not just the gravel that's creatively sourced. John's concrete uses a material that would otherwise be regarded as waste, upcycled fly ash from the coal industry. And this, slag, a byproduct from steel production. But the main green innovation is in the chemistry. I've come to the company's lab to meet Russell Genrich, who helped develop it.
Russell. Nij. Good to see you.
First, I want to know why conventional concrete has such a big carbon footprint. And the main reason is something called Portland cement. So what's the difference between conventional concrete and geopolymer concrete?
For normal concrete, Portland cement is the binder that binds it all together. That contains clinker, quarried as limestone, that is burnt in a rotary kiln at high temperature, releasing carbon dioxide.
So to make clinker, you're getting limestone out of the ground and then burning it, essentially.
That's right. There is quite a large amount of carbon dioxide that is released, and that's a fundamental part of the manufacture of Portland cement.
So it doesn't matter how you fire it, whether it's with wood or gas or solar panels, doesn't matter.
You still have that large carbon dioxide release as you're calcining the limestone.
So the production of clinker is one of the most carbon-intensive industries that we have on the planet.
Certainly, yes.
But your product, the geopolymer concrete, doesn't involve clinkers.
That's right.
Because producing green concrete doesn't involve cooking limestone, it doesn't release large carbon emissions like conventional concrete. But it does need an extra special ingredient.
We then add a chemical activator to that to make it behave like normal concrete.
The ingredients of the activator are top secret, but Russell can tell me that it doesn't need heating either. And so that activates those two ingredients at room temperature?
At room temperature, yes.
To form the binding cement?
That's right.
By putting waste and byproducts to good use and removing limestone, this geopolymer concrete joins the growing number of new materials that engineers can now use. But can green concrete handle the full weight of an aeroplane? I'll catch up with John and his team on the taxiway later. Building greener cities is about making them resilient, productive and sustainable, now and for future generations. And alongside energy and infrastructure, there's also new thinking around how we plan and construct our built environment. The challenge is, can we keep going up with less cost to the planet? Throughout history, changes in how we build our cities have been driven by the development of new materials. From wood and brick to steel and glass. And the next wave is taking us back to the beginning.
Level 6.
Thanks, mate.
Welcome to Daramu House.
Thank you.
This is level 6. We're now in a building which is all timber from level 1 up, including the lift shaft, the columns, the beams and the walls and floors.
So from level 1 up, there's no concrete or steel?
That's
100%,
correct.
all timber.
That's incredible. This is special timber, engineered timber.
Special mass engineered timber which we erect on site. Why don't we take a look?
Sounds great. Meaning treehouse in the Gadigal language, Daramu House is one of only a handful of multi-storey engineered timber office buildings in Australia. And to make a building like this, you need 3 kinds of engineered timber.
So this is a pretty good example of where we can see our 3 product types or mass engineered timber types.
So these bits of wood, they're all different. They're all different types of timber.
You're looking at 3 different elements. You're looking at your glulam primary beams, your glulam joists and your CLT floor slab, which spans between the joists.
The CLT, or cross-laminated timber, and the glulam elements are made up of pieces of timber glued together to replicate the strength of concrete and steel. What's the difference between the types of timber?
Yeah, good question. The CLT has grain structure running in 2 directions and we pancake them together with glue and that produces a element which is stiff in 2 directions. Whereas glulam, all the grains are running in 1 direction from end to end, which works pretty well for long spans such as beams and columns.
So what about the cross beams?
So, unlike a concrete building where we use walls for shear walls and stiffness, in a timber building we tend to use bracing bays. So those K braces that you see there and also here are giving us lateral stability, which responds to the wind loads or seismic loads that the building might endure.
This timber building can withstand high winds and earthquakes as much as the steel building next door. And because the elements are prefabricated, engineered timber is very versatile.
We love it. From a fit-out perspective, you can see we don't do anything to it. We just leave it the way it is. There is no ceiling, there is no plasterboard. In fact, everything here is a finished product.
So they're all cut off-site to shape, is that right?
Correct, they're processed off-site. Putting it in was a lot easier, we found, than structural steel. It's very easy to grab a battery tool and shave a little bit of timber off the side to make it fit nicely, compared to grabbing a gas axe or a grinder and having to cut it and hot works and things like that.
How do the guys on the tools feel about working here? Yeah.
I loved it because, I mean, it's unique for one. It's not something you get to do a lot of. It comes together quite quickly. You can sort of finish one shift and look back at how much structure you've whacked up in that day, and it's quite a good feeling to see half a floor's finished in a day.
But is there a limit to how high you can build with timber?
This one is. So this is our roof, our top floor of the building. We've only come up ground plus 6 floors in this building because we have planning limitations on how high we could go. But ultimately we feel comfortable to go up to 15, 16 floors without thinking too hard.
So that's about double this height you could go with timber?
Quite happily. We've got to remember, the vast majority of people work below level 10 around the world, and even in the cities like this. It's just the CBDs where you have this conglomerate of tall, high-rise buildings that we go really, really high. But this caters for a major part of the market.
So is this timber more expensive than the concrete and steel that you would use to make it?
Look, right now we are slightly more expensive than concrete, but the gap is closing rapidly. Indeed, a project we're looking at the moment in Australia, we expect it to be line ball, timber and concrete. We're getting better at using the material. We're using less of the material per square metre. We're building it faster. It's like anything. We're on that steep learning curve. We've still got a long way to go, but we're already starting to see real benefits commercially to go down this pathway.
So how much wood is in this building and how long would that take to grow?
In this building is around about 4,500 cubic metres of CLT and glulam. We know in Australia our forests are plantation softwood forests, grow at around about 30 cubic metres a minute. You can do the numbers, we can grow one of these buildings in less than a day very happily.
If that's true, we could start to see more of these types of buildings on our skylines.
Concrete and steel started 200 years ago, and timber's revived in this space because we have the mass-engineered timber technology that we didn't have previously. It's the only renewable material we have, and in a market which is demanding a more carbon-responsive behaviour, and what better way to do it than building our structures out of timber.
This wooden building is architecturally beautiful, but engineered timber has challenges to overcome if it's to be widely used to build greener cities. While it's been proven that it can be just as safe as steel in a fire, it's more expensive than traditional building materials. And I want to find out if it's truly sustainable. I'm back in Queensland's high country and at the site of one of the biggest applications of green concrete. I'm keen to see how John's taxiway has set.
So how's the pour going?
Pours went really well. We've just finished. We've just driven off the end of the 100 lineal metres that we'd planned to do today. But yeah, it went really well today.
100 metres in a day?
100 lineal metres times 4.5 wide, so obviously 450 square metres.
Across the airport, 8,800 tonnes of CO2 emissions have been saved by using geopolymer concrete. That's about the same amount as 407 average Aussies produce in a year. But there's always a trade-off.
What stage of the process are you up to now?
It may be clean and green, but it needs some extra attention to help it cure properly, in the form of a blanket.
This concrete has a very low heat of reaction, so we need to be careful of the thermal changes in length. So on with the geotextile, that keeps the day's heat in, it keeps the evening cool out, and then in the morning when the sun comes over the hill, you don't get that thermal shock, which rapid expansion wants to crack it.
This ensures the taxiway has a smooth surface. But is it hard wearing?
This slab here is designed to hold planes. How do you know that it's going to be strong enough?
Geopolymer concrete that we're using here is about 30% stronger in flex or tension than typical concrete. The whole basis of these pavements is flexural strength. The reason for that is that it has better bond to the aggregates and therefore it grips better.
Up on the hill behind the airport, John can show me what he means.
So this is where you test your materials?
Yep, this is our field laboratory. Been here for 5 years. We test all our materials here.
So you're testing samples every day?
Yeah, every day. It's a full-time operation for all of our components. This one's already been tested. This is this morning's run. As you can see, we're breaking them in half.
It's literally green.
Yes, correct. It's a natural process of the GGBS hydrating.
What's that? What's GGBS?
GGBS is the slag that we talk about. So it's 80% of the binder component. As it sets and matures, it creates a green colour.
So there's iron in the binder?
Steel, yes.
Steel in the binder?
We're about to put concrete poured 5 days ago to the test.
All right, so these are tested in this machine over here.
And to see if it can carry the weight of a large jet.
We're actually measuring the amount of force it takes to fracture this sample down the middle.
So you're measuring strength in this direction?
In tensile, right?
Concrete takes 28 days to set to its full strength, so this sample is still in its infancy.
Putting constant pressure at a measured load rate.
We're starting to read now.
Now you're starting to read.
The compressive strength of concrete is measured in megapascals, or MPa.
Now running 0.34 MPa.
We're aiming to get over 4.8 MPa. That means it'll be safe for planes.
You can see it bend a little, actually.
Yeah, it will. So peak stress, just about 6 MPa flexural strength, which is about 20% higher than it needs to be at only 5 days of age.
6 MPa is equal to more than 600 tonnes of force per square metre. A lot more than a fully loaded 747.
So this is stronger than it needs to be under the standard?
It's already exceeded by approximately 20%, the 28-day requirement at 5 days of age.
So it's greener, faster and stronger?
Correct.
When it comes to concrete, it might be that seeing is believing.
The more we do ourselves, the more it's out there in the market. So the guys you see out there today, they're favourable of it. Of course, they're going to have a few beers with their mates. The words gets out. You don't need to be scared of this stuff. It works. People get used to it.
It's fair to say that we'll be using a lot more concrete in the coming years. But innovations like this are cause for some optimism.
It's quite obvious around the world that not only the CO2 generated by the production of Portland cement, but other things are running out. You know, limestone's an exhaustible commodity in countries like India. They will not be able to make ordinary Portland cement sometime in the near future. So the challenge is to find a material that can replace the ordinary Portland cement and at the same time make it sustainable. So yes, we're at the start of what's going to be a long road, but we would hope it's building steadily over the next few years.
A long road or a long taxiway?
Either. The longer the better.
Concrete is one of the most used resources on the planet.
If the industry got behind green concrete, carbon dioxide emissions from the industry could be cut by up to 2/3.
There's no simple answer to how we build sustainable cities, but new thinking in materials science will help make them more resilient. On Queensland's Fraser Coast, I've come to the Tulare Forest. It's plantations like these that are growing the next generation of multi-storey building. I want to find out how many office blocks this forest can grow, and whether engineered timber is truly sustainable.
Hey Nij.
Hey Shona.
How are you?
Good to see you.
Yeah, you too. Welcome to our plantation.
Shona Heading is a forestry steward and a specialist in softwood plantations.
So what we're looking at here is southern pine plantations. The trees you see behind us are around 30 years old, so they're just about ready to be harvested.
Yeah, right. So how many buildings are you growing here?
Well, we can produce about 160 of those kind of 6-storey buildings every year.
160 6-storey buildings
Every year.
So it's almost one every couple of days.
Yeah, we can sustainably harvest around 2 million tonnes of timber a year out of our plantations.
That's amazing. 2 million tonnes a year is a remarkable growth rate, especially compared to the thousands of years it takes to form limestone and iron, the two major components of concrete and steel.
Are you seeing more and more of this product going into the engineered timber products?
I think there's absolutely a future, an exciting future for engineered timber products. We're currently working with our geneticists to grow timber that's stronger for these engineered timber products.
Oh, right. So these aren't just the standard
These
pine
are
species?
not standard pine species. So this is a locally developed hybrid, so a mix between Pinus elliottii and Pinus caribea, and they come together with the best properties to produce our southern pine hybrid, which is really tolerant to our climate. Okay, this looks like a good spot.
Alrighty.
You want to dig a small hole with your spade?
Sure.
So that.
That's perfect. There we go.
So do we need to water or fertilise this guy before we go?
No, so we've had decent rainfall, so we only plant when we've had good rainfall with follow-up rain, and they're watered well in the nursery, and in the nursery they actually cut off the water supply slowly, so they're used to droughted conditions.
So they're ready to grow?
They're ready to go, yeah. We actually retain some of this fine debris along the harvest site, which actually puts some nutrition back in the soil for them.
Sure.
This seedling will fend for itself for the next 30 years, continually storing carbon from the atmosphere, even storing it after it's harvested. At this end of the life cycle, watching the machines make quick work of 30 years of growth is captivating. From the feller buncher that fells and bunches the trees, to this machine here, the processor, that cuts and measures. Operator Stacey lets me take a closer look.
Copy there, Stacey.
Yeah.
Down tools for a sec, we'll come over for a chat.
Come up the front of the track and make sure you're hanging on 3 points of contact.
All right. All right.
Yep, good.
Hey, mate.
Hello.
Hi, good
How
to see
are
you. Good. I know that the stems themselves weigh about a tonne, but it looks like a really delicate operation. What's it like to operate that arm?
You've got to be very careful. The bigger the tree is, the more fragile it is. So you've got to rest it. So when you cut them, they don't actually split. They seem to be drier for some reason.
How many do you get through a day?
Usually about 1,200 trees a day.
1,200 stems a day. What's your record?
1,980 in an 11-hour shift.
That's pretty good, eh? Good one. Do you ever think about the buildings that these are going to become part of?
Yeah, I do actually.
Yeah.
I think that it's actually going to something that people are going to be living in. Good, really good.
The logs Stacey processed are off on the next stage of their journey. And I'm hitching a ride with them on the logging truck. This sawmill is in Queensland's Tuan Forest, where the production of engineered timber begins. Showing me around is manufacturing manager Dave Bennetts.
Hey, Nij. Hey, Dave.
Driving in style, I see.
Yeah, always like this.
Top it off.
Nice to meet you.
Here's the safety gear for the day.
Thank you very much. Got it, perfect.
Pop that on.
Alrighty.
The glasses on. Let's go and show you how much we love timber.
That sounds great.
This is a far more complex process than I was expecting. From when they first arrive, these logs are meticulously studied, sorted, and graded for structural quality, before making their way here to the mill for sawing.
So beneath our feet here is a three-dimensional laser scanner.
Yep.
It's taking a geometric profile of that log and determining how best we set it up to put it through the saws.
So coming in on this end is the log, and then coming out on the other end are the boards of all different quality and timber and size. And
quality, shapes and sizes. So they've been in the bush for 30 years growing away. You know, we process them in under 4.5 seconds. So it's all about trying to maximise the product that we can get out of the log rather than generate sawdust.
The processing of the wood is unrelenting. Log after log is measured and sliced with speed and accuracy.
where does your highest quality timber go?
Into engineered products. There's no doubt about that. If you look around this building here, it's made out of our glue laminated beams, so that's really the target market for our really stiff material that comes from the outer part of the log.
So this building is made out of engineered timber?
Yeah, absolutely.
Seeing the timber here has given me a newfound respect for the pine bed frame and desk of my youth.
So how long have you been working here, Dave?
Oh, 30 years now, Nij. I started in '89 as a timber cadet and pretty much been here ever since. I love it.
It's about as long as it takes to grow a tree.
Exactly the same amount of time. I should see them coming through any day now.
This milled wood is strong, but not yet strong enough to hold up a multi-storey office block. So I'm keen to see this softwood transformed into the tough stuff. Up the road in Maryborough is where it all happens.
Come this way. So this is the vacuum de-stacker that unloads the wood for us.
Simon Preble manages this engineered timber facility, which specialises in the production of glue laminated timber, also known as glue lam.
Alrighty, Simon, so what are we seeing here?
Yeah, so this is our new glue lam production facility. And what we do here is take the wood from the mill in Chuan, and we're processing that to glue it together to make a beam of a precise known strength and a precise dimension.
So it looks pretty new. It looks like you guys are still setting up here. Where is this production facility at?
We see a great future for glue lam. There's a really growing market, and so we've invested in this new facility. We're actually just commissioning it now, so we're about 2 weeks into running the plant. We've just made our first couple of beams, so it's an exciting time for us, but yeah, it's brand new.
Such serious investment means a massive bet has been placed on the future of engineered timber.
One of the changes with this plant is a move to a new type of glue that doesn't require any heat, so it's a much quicker curing, gluing process.
The secret's in the sauce.
Exactly.
The old glue took up to 6 hours to dry, while this new glue dries in just 10 minutes. And because it's a less energy intensive process, fewer greenhouse gases are released into the atmosphere.
Gee, Nij, welcome to our testing facility.
Oh, thank you.
The new glue might be more efficient to produce, but does it perform well?
John.
Rightio, so over here we've got the shear rig.
John Irwin and Dr. Henri Baylorez are going to test if the glue is strong enough to withstand the weight of multiple stories.
Basically, we're going to try and sever off this bit of timber here right at the glue line.
And seeing if the glue's stronger than the wood.
Yeah. Do you want to go?
Yeah, let's do it. That's 1 kilonewton. 100 kilograms, right? That's 1,000 kilograms. Whee, there it goes.
Rightio. So we have 1.8 tonne.
1.8 tonne of weight on that timber across the glue face.
Correct.
That's the weight of a delivery van.
But then what we want to see is where it broke, is that right?
Yeah, that's right. Let's go check it out.
Under intense pressure, the glue lam has broken. But to understand whether it was the wood or the glue that failed first, we need to use a UV light. The glue fluoresces under UV, so if it failed in this test, we'd expect to see lots of blue fluorescence.
It's pretty good.
It's very good. You have a little bit of glue, but because we cross the glue line, but it's probably 95% of wood. Good news.
So it mostly broke along the wood?
Yes.
Good news.
It may be strong, but there's been some debate about whether engineered timber is truly sustainable. On the positive side, wood stores carbon long term. But the process of logging and creating engineered timber produces greenhouse gas emissions. And monocrops and poorly managed forests can reduce biodiversity. So there's lots of potential, but it does depend on how we do it. The skylines of our cities are dominated by tall buildings. Last year alone, 43 new office and apartment towers were built across Australia. And the higher we build, the more expensive and resource heavy they can be to maintain.
Long way down.
It's a long way down if you're not in a machine.
Whether the buildings of the future are made of timber, concrete, or even steel, one thing's for certain, they'll all be covered in glass. Only problem? Glass gets grubby.
I'm dangling by a few wires 56 stories above the city streets to access some dirty windows. And cleaning them, I'm about to learn, isn't as easy as it looks.
Wet your mop up. Not too much water, that's way too much. Because everything that goes on there has to come off.
Oh yeah, I see.
Even when it rains on a building like this, you need someone like Matt Patis to clean the streaks and dirt off later.
So have a go?
All right.
Have a go. Not too bad for the first time, but you could tell that you're new.
Ah! So how long does it take to clean this building, Matt?
It depends on the weather. Mostly the wind is a very big determining factor. We might clean a whole side of a face of a building, but then a week later, it's got dirt and dust on it once again. So it's never ending.
Do you think that architects and designers are thinking about maintenance when they're creating these buildings?
Well, I don't really think they are. Funnily enough, I think it's an afterthought. Some buildings are much harder to clean because of the way they've designed them.
There was a time when people thought self-cleaning glass was the answer. But so far, durability has been a problem. Now, an Australian invention might be the answer. A new coating has been engineered that mimics nature's ability to keep itself clean. The lotus leaf has one of the most repellent surfaces in nature. Scientists at the Australian National University are using biomimicry to imitate its surface.
Antonio.
Hey, Nij.
Good to see you.
Good to see you too.
Professor Antonio Tricoli leads the team of researchers.
Right, please come over.
So you can achieve the same effects of a lotus leaf with the materials in your lab?
Yeah, actually I think we can achieve something slightly better. And I'm going to show you some demonstration. This is...
Antonio is going to show me the difference between two coins, one covered in his new coating, the other not.
And if you put it in water, it will just sink, as you would expect it from any coin. Now, the interesting thing is that if you put a coin that has been coated with our super hydrophobic layer, it does not sink, but actually it opens the water.
Oh, wow. That's great. That's unlike any 20-cent coin I've ever seen.
The parting of the water is aptly named the Moses effect. The water-repelling ability of this coating is so strong, it keeps dry even when it's immersed in 5 millimeters of liquid.
In some sense, you can imagine as water flying over a layer of air above your surface. So when you have a super hydrophobic surface like this, basically the water is flying on it. It's not touching it at all.
Unlike surfaces that chemically bond with water and make it stick, the surface of a lotus leaf does the opposite. Water runs off the surface, taking with it any dirt or dust, effectively cleaning the leaf.
So what we're looking at here is the nanostructure of the lotus leaf.
Exactly. So we shoot beams of electron to surfaces, and in this case, we look at what comes back.
So the scale bar here is 200 nanometers.
Yes.
It's smaller than the wavelength of UV light.
Significantly smaller, and the particles actually are around 5 to 10 nanometer.
These tiny bridge-like structures create air pockets, and it's these air pockets that prevent the water from touching the lotus leaf's surface.
So you're trying to replicate this kind of surface with your materials?
Exactly. Now, replicate what nature does is not always easy, as you may imagine. So actually
One of the key challenges faced by scientists developing repellent coatings is how to make them durable. Antonio believes his new material solves this problem.
So what's the coating?
Well, the coating is made of two components, PU and PMMA. One is a polymer, actually this one, that we have engineered here at the ANU.
It's a special mix of polymers so strong, it's considered a potential coating for bulletproof glass.
And the other component is actually made of silica. Silica is very pure sand, the purest sand that you can imagine. And then we functionalize this sand on the surface with something that makes it less likely to want to touch water. So basically an hydrophobic surface.
Can we see how it's coated?
Sure, let's come over, we'll show you how we do this.
Apparently, this complex innovation can be easily applied. With little more than a tool used for painting fingernails, which means it can be used in a wide variety of applications. The polymer goes on first, and then the silica particles.
Well, this is the coated.
Yep.
And this is the initial uncoated glass, so a normal glass surface.
You can see the coating on it. Is there a way to make it transparent?
Well, that's what we're working on. So this is still work in progress that I'm not allowed to show you completely, but basically we can make surface that you're not able to see by naked eyes.
Incredible. Is there any limitation on what you can coat?
Actually, this coating is interacts with surface freely, so there is not a chemical interaction. And this means that you can actually apply it to anything. We have applied it to glass, obviously, plastic, wood, bricks, and even paper.
It's incredible. Even paper?
Yeah.
A coating that can be used on any surface to repel water, dirt, and pollution is a big achievement. But is it really more durable?
But the question is, how do we know how stable they are? So this is a tab abrasion. It's a standard test to take the durability of surfaces when subjected to rough conditions, mechanical conditions. Now, if I give you a demonstration, I'll put down our table abrasion instruments.
The test is like rubbing sandpaper over the glass 300 times.
And basically simulates what happens to a surface when it gets rubbed in real life.
Time to see if it still works.
So what you see here is the water droplet making almost a perfect sphere on our surface, which basically tells you that the surface is very water repellent.
So even after the testing, it's still repelling the water?
Yeah.
That's great.
This could solve the problem of durability.
So how long do you think it'll be before we see this across our cities?
Well, my hope is that we will see it coming into various applications, but perhaps in the next 3 years, it could be a good horizon for such technologies.
Great. This super hydrophobic coating has a way to go before windows across our cities are self-cleaning. But it's about more than just self-cleaning. It's about looking after things like windows so that they last longer, treating all materials in our built environment as precious so that they can continue to serve their purpose long into the future.
It's been over a month since I first had a chance to explore Australia's most ambitious transport network. Since then, 5 enormous tunnel boring machines, or TBMs, have continued tunnelling across the city. It's a hive of activity.
Alright, TBM 1, so you'll be cutting, so you'll be going down, you'll have to finish off that regrip, and then you'll be straight into a regrip after that, so we can just check your grout, you've got a fair bit of grout.
This could get people off crowded streets and down underground instead.
Alright boys, is that pretty clear?
I've come to see how the project is progressing.
Christian.
G'day Nij, welcome back mate.
Yeah, good to see you.
Yeah, good to see you again.
How's it been going?
We're going fantastic, yeah. Fair bit of progress over the last few months, so getting really close towards the other end there at Barangaroo now.
Can we have a look?
Absolutely.
I'm keen to go down.
Just before we do, we're going to have to do one thing though.
What's that?
I'm going to introduce you to a guy called Jerry, and he's going to explain some of our safety protocols.
Right, Jerry.
Hey Jerry.
Are you going underground?
Sure am.
Mate, it's company policy that we shave before we go down.
Shave my beard.
Everything's got to go off. We need the dust mask to sit right close to your face to protect you from the silica in the tunnel. So you have to shave before you go down.
Everything's got to go. All right, well I better get to it.
Go and do it, that's sorted.
I'll see you in a teacher.
All right,
Thanks, Jerry.
Thanks, mate.
No one's seen me without a beard for years.
Alrighty.
So this is quite a commitment.
Looking good, mate.
Thank you.
Nice and fresh.
Thank you.
This will fit on perfectly now, so there's your dust mask.
Lovely.
But yeah, your kids won't recognise you.
No, they'll freak out.
Okay. Let's go.
We're off to see the action, which is all happening under the heart of the city.
Yes, it's a fair old trip in, about 7 kilometres in.
Are we following the train line?
We'll go through the metro tunnel. This is exactly the alignment of the metro.
Yeah, wow. Some of the first passengers, I guess, through the tunnel.
First passengers, yeah.
Mask on.
This tunnel is being built to manage 40,000 commuters per hour. To find out how that's possible, Christian's dropped me off at Martin Place, where I'm going to chat with tunnel designer Stuart Simons.
Stuart! How are you? Good to see you. Yeah. This is incredible. Can you show us some of the things that you've designed?
Yeah, come this way and have a look.
Great.
This is just one of 31 stations being built around the city to move people off congested roads and underground.
So Stuart, I think I saw the tunnel boring machine break through over there.
That's right. The tunnel boring machine from Marrickville broke through at that end, and now it's moved up to the end of the station there and is relaunching towards Barangaroo.
So it's keeping going on that way?
It keeps going that way for several hundred metres.
Yeah, wow. It's changed a lot since I was here. That certainly wasn't there.
No, last time you were here, that was all solid rock. That shaft there is 26 metres deep. That'll allow pedestrians access into the station cavern here.
So, not long from now, there'll be streams of people coming in here and catching their trains wherever they're going around Sydney.
In the very near future. So the way that this is being configured at the moment is trains running at 4-minute headways. The signalling capability allows trains to run at 2-minute headways. So what we're designing for now can be doubled with very little effort.
So we're designing this network now for the amount of passengers that Sydney is going to be expected to have for the next 100 years.
That's it.
Are tunnels the future?
Absolutely. Tunnelling is a great way to extend the network. It has minimal impact on all our surface people. Road networks are busy at the moment, and taking up road networks to build light rail or bus networks has an impact. The ground use that we can achieve by building underground is immense. It's only limited by our imagination.
This 7-kilometre long tunnel was excavated and reinforced by a TBM using thousands of prefabricated rings. Weighing 4 tonnes each, the segments are poured and cast on the surface using conventional concrete. As we know, concrete has a high environmental cost, but the whole system is being built to last at least 100 years.
This is the backup of the TBM. We've arrived now, so we'll jump out here and get up onto the walkway.
Christian and I have just arrived at the tail end of a TBM called Nancy.
Thanks, Conrad. Thanks, mate.
This 160 metre long machine has been purpose-built to tunnel through Sydney's shale and sandstone. She's already excavated more than 821,000 tonnes of rock. Complete with all the mod cons, the TBM has a toilet, rescue pod, even a dining room, where I get to meet some of the crew.
G'day guys, how you going?
Like electrician Joshua Fogarty.
What's it like to work underground?
Oh yeah, it's not too bad. At first it's a little bit daunting when you kind of think of it as this big closed area, but once you're down here, the 7 metre diameter, you don't really notice it, you don't really think about it.
So you guys do you work at the front end or the back end?
I'm the electrician, so I work everywhere, so whenever something breaks.
So Christian was telling us that I think the capacity of the station is like 40,000 people per hour. Do you guys think about that when you're working on it?
You kind of think when you're on it, it's kind of cool building something that later in the future you'll be able to kind of ride yourself and kind of say, yeah, we built this.
It's time to check out the business end of the TBM, the moment I've been waiting for.
So up here's where all the action occurs. This is where we build the segment lining, put those rings together.
The concrete segments are built to withstand continual pressure from the ground and buildings above, even the weight of future developments. Using a force of 300 tonnes, the segments are lifted into place.
So once it's into place, how do you fasten it to the other segments?
We have dowels that join ring to ring. So there's 2 dowels for each segment to join the ring to the subsequent ring. And then each of the 6 segments are bolted together with a spear bolt.
While it excavates and builds, the TBM also propels itself forward at 3 kilometres per hour.
How far will the TBM move today?
We normally do about 40 metres a day on average. Our best day is 86 metres, but a typical day is about 40 metres, which includes building 25 of these rings.
Do you think about future generations as you're working on the tunnel?
Absolutely. You know, I've got 3 kids, and for the people of Sydney and for the kids, the transport that we're building is absolutely fantastic.
A machine that simultaneously digs, clears and builds is a clever solution to tunnel engineering. As long as you can afford it. Whether it's the development of smarter materials,
You can tell that you're new.
or engineering systems that create vast spaces under our feet,
Alright.
Yep.
it's clear that there are no quick fixes when it comes to making sustainable cities. It's going to be a tricky balancing act. Technology plays its part, but so do many other things.
We see a great future, so it's an exciting time for us.
I'm excited by some of the things I've seen.
You don't need to be scared of this stuff. It works.
These solutions all have their part to play, with consequences beyond what we can imagine. Green concrete can help build our future cities with significantly less impact to our planet and climate. But our future can't rest on one or even a handful of solutions. Thousands of ideas are needed, and they'll need to work together.
But all these smart people living in cities, they'll come up with something.